Again, welcome to Operating System CS332 class. These lectures cover process description and control. Now, before we define the term process, it is very useful to summarize some of the concepts we introduced in our previous lectures. For example, what is a computer system? Here we see a computer platform consists of a collection of hardware resources, such as the processor, the main memory, the I/O modules, disk drivers, and timers, etc. Also, the computer applications are developed to perform a specific task. We also have the system programs such as operating system, which is again a special software that interacts with the computer hardware. So it is very inefficient for application to be written directly for a given hardware platform. Now, the principal reasons for this is as follows. Again, numerous applications can be developed for the same platform. It makes sense to develop a common routine for accessing the computer's resources. Also, the processor itself provides only limited support for multi-programming. So again, software is needed to manage the sharing of the processor and other resources by multiple applications at the same time. Also, when multiple applications are active at the same time, it's very necessary to protect the data, the input-output usage, and also other resources that use for each of the applications. So we can think of an operating system as providing the uniform, abstract representation of resources that can be requested and accessed by application. Also, operating system was developed to provide a convenient, feature-rich, secured, and also consistent interface for the applications to use. So it's very, very rare that and very complex to develop a computer application that will interact directly with the computer hardware. So again, we can think of as operating system as providing the uniform, also the abstract representation of resources that can be requested and accessed by applications. Now, resources including, as we said earlier, the main memory, network interfaces, the file system, and so on. Now, once the operating system has created these features, abstractions for application to use, it must also manage their use. So the operating system also interact and also manage all the computer resources. So for example, an operating system may permit resources sharing and also resources protection. Now, operating system also is a management of application execution. So now that we have the concept of applications, system software, and resources, we are now in a position to discuss how operating system can, in an orderly fashion, manage the execution of applications so that one, the resources are made available to multiple applications. Second, the processor is switched among multiple applications, so all will appear to be progressing. And lastly, the processor and I/O devices can be used efficiently. So these are one of the main objectives of, again, operating system. The processor and also the I/O device can be used efficiently. This approach is taken by all modern operating systems, and they normally rely on a model in which execution of an application corresponds to the existence of one or more processes. Now, we can recall in our previous lecture that we suggest several definitions of the term process. We said earlier that a process is a program in execution. Also, a process can be an instance of a program running on a computer. Or also, it can be the entity that can be assigned to and execute on a processor. Now, the two essential elements of a process are the program code which may share with other processes that executing the same program, and also a set of data associated with that code. So a process or a program is an instruction or the code that is written and is saved. Now, a process will be a program that is being executed. Now, in order for a program to be executed, it needs a data to use. So the data that are associated with the code is also the concept. So when the processor begins to execute the program, we refer to this executing entity as, again, a process. Now, what are the process elements? Here we can say also that at any given point in time, while the program is executing, the process can be uniquely characterized by a number of elements. And these are the elements, including the following. We have the identifier. The identifier will be the unique ID that associated with the process. And this will distinguish from other processes. So any process has a unique ID number or identifier. Also, the process may have a state. So this state will be if the processor is currently executing, or if it's in a running state, or if it's waiting. So the state will tell us where the processor is. First, again, the identifier, unique number, and the state, and also the priority. Priority level related to other process. Then the program counter, which is normally the address of the next instruction in the program to be executed. So program counter helps us to maximize the utilization of the processor. It normally points to the next instruction to be executed. We also have the memory pointers. The memory pointers normally include the pointers to the program code and data associated with this process, plus any memory blocks shared with other processes. We also have the context data. These are the data that are present in registers in the processor while the process is executing. Then we have the I/O or input-output status information. This will normally include the outstanding input-output requests or input-output devices. The example can be the disk drive or the hard drive and assigned to this process, and also a list of files in use by the process and so on. And lastly, the accounting information. Normally, the accounting information may include the amount of processor time and also the clock time used, the time unit limits or account numbers and so on. The next is the process control block. Now, we said the information in the preceding list is stored in a data structure, typically called the process control block. So process control block, we can see, consists of the process elements, as we discussed in the previous slide. We have the identifier, the state, priority, program counter, memory pointers, context, data, I/O status information, and also the account information. So if the process control block consists of all the process elements. Now, the significant point about the process control block is that it contains sufficient information so that it is possible to interrupt a running process and later resume the execution as if the interruptions had not occurred. So the process control block, again, is the key tool that enables the operating system to support multiple processes and also to provide for multiprocessing. Now, when a process is interrupted, the current values of the program counter and also the processor registers, which is the context data, are saved in appropriate fields of the corresponding process control block. So here again, the whole concept, when a process is interrupted, as we said, the current value of the program counter and the process registers are saved in appropriate fields of corresponding process control block. And also the state of the process is changed to some other value such as a block or ready. Also, the OS is now free to put some other process in the running state. The program counter and also the context data for this process are loaded into the processor registers, and the process now begins to execute. Now we have different types of process states. Here we can say, as we discussed earlier, for a program to be executed, a process or a task is created for that program. So from the processor's point of view, it executes instructions from its repertoire in some sequence dictated by changing values in the program counter register. Now, over time, the program counter may refer to code in different programs that are part of the different processes. So from the point of view of an individual program, its executions involve a sequence of instruction within that program. Here we can also demonstrate characterizing again the behavior of an individual process by listing the sequence of instruction that executes for that process. Now, such a listing is referred to as a trace of the process. We can characterize behavior of the process by showing how the traces of various processes are again interlinked. So here we have the trace, that's the behavior of an individual process by listing the sequence of instruction that execute for that process. And also the behavior of the process can be characterized by showing how the traces of various processes are interleaved. Dispatcher will be a very small program that switches the process from one process to another. So we have again the concept of process execution. Normally, execution always takes place in the main memory. So we can see from the diagram here, we can see we have the main memory, and we have a process A, B, C, and there's a space between the brown area space, and also we have the dispatcher in the main memory and the program counter, which will again point to the next execution. Now let us view that traces from a processor point of view shows the interleaved traces resulting from the first 52 instruction cycles. For the instruction cycles are numbered. Now in this diagram, the shaded areas represent the code executed by the dispatcher, the shaded area. And also the same sequence of instructions is executed by the dispatcher in each instance because the same functionality of the dispatcher is being executed. Now we are assuming that the operating system only allows a process to continue execution for a maximum of 6 instruction cycles, after which it is interrupted. So again, this prevents any single process from monopolizing the processing time. As the figure shows, the first 6 instructions of process A are executed, followed by the timeout and the execution of the second code in the dispatcher. So again, we are assuming that the operating system only allows the process to continue execution for a maximum of 6 instruction cycles, after which it is interrupted. Now, this prevents any single process from monopolizing processor time. As shown again, the diagram, the first 6 instructions for process A are executed, followed by timeout and the execution of again the second. So again, from this simple model, we can already begin to appreciate some of the design elements of operating system. Each process may be represented in some way to that, that the OS or the operating system can keep track of it. So this is again the two-state process model. When a new process is to be added to this currently being managed, the operating system builds a data structure that are used to manage the process and also allocate addressing space in main memory to the process. Now we describe this data structure in section 3-3. This action continues the creation of new process. Now, for common links to the creation of process as indicated in table 3.1. In a batch environment, a process is created when a new user attempts to log on. Now, in both cases, the operating system is responsible for the creation of the new process. An operating system may also create a process on behalf of its application. For example, if a user requests that a file be printed, the operating system can create a process that will change the printing. So here is the enter state. So when we enter the two-state process model, we enter not running, then we dispatch to the running state. We can pause it and come back to not running. Other than that, we exit. So this is the queuing diagram. And this example, the queue program. And so the item goes to the queue dispatch. If it's the required data, then again, we process it and that's it. If not yet finished, then we go back, pausing and go back again. So now what are the reasons for process creation? So here again, we said that any computer system must provide a means for a process to indicate its completion. So a batch job should include the halt instructions on an explicit OS system called for termination. Now, in the former case, halt instructions will generate an interrupt to alert the operating system that a process has completed. So again, that's the new batch job, and we also have the interactive logon. Here, the user at the terminal logs on to the system. Then we have created by OS to provide a service. Normally here we have the OS can create a process to perform a function on behalf of the user program without user having to wait. Then spawned by existing system. We have, for the purpose of modularity or to explore parallelism, a user program can dictate the creation of a number of processes. So we have the process creation, we have the process spawning. We also have process, parent process, and also we have the child process. Then we also have the process termination. So in this case, again, there must be a means for a process to indicate its completion. A batch job should include the halt instructions or an explicit OS service call for termination. Now, for interactive application, the action of the user will indicate when the process is completed. Now we have our 5-state process model. First, we start with the new. So with the new, which is also ready, from new to ready, the operating system will move a process from the new state to the ready state when it is prepared to take an additional process. Now, most systems will set some limit based on the number of existing processes or the amount of variable memory committed to existing process. So the limit assure that there are not so many active processes as to degrade performance. So the next will be the ready. So the ready to exit. So here we have new to ready, and we also have ready to exit, or ready to running, which is dispatch, or running to ready, which is timeout. So again, with the ready, when it is time to select a process to run, the operating system chooses at least one of the process in the ready state. This is the job of the scheduler or the dispatcher. Scheduling is explored in part 4. So we also again have the running state to block. So normally from the new, we admit to a ready state, then we dispatch to running state, maybe an interrupt may happen, then we come to timeout, back to ready state. Or we may go to event to wait and to block. And from running, if everything went through, we release it to again, then exit. So we have 5-state process model: the new state, ready state, block state, running state, and exit state. We also have the concept of suspended process. And here we should understand the concept of swapping. So again, swapping involves moving parts of a process from main memory to a disk. So we are swapping the program or data from the disk to main memory or memory to a disk. So we should recall that the reason for all of this elaborate machinery is that I/O activities are much more slower than computation, and therefore the processor, again, in a given programming system, given unique programming system, is idle most of the time, but the program of figure 3.8 does not does not do that entirely solve the problem. So it is true that in this case, memory owed multiple processes, and that the processor can move to another process when one process is blocked, but the process is so much faster than I/O that it will be common for all of the process in the memory to be waiting for I/O. So even with multi-programming, the processor could be idle most of the time. Now what to do? Main memory could be expanded to accommodate more process, but there are two flaws in the approach. First, there's a cost associated with the main memory. And also another solution is swapping, which involves the moving part or all of the process from main memory to disk. Now, when the use of swapping, as just described, one other state must be added to our process behavior. Also, the suspend state, when all of the process are in main memory, are in the block state, the OS can suspend one process by putting it in a suspend state. So here we said that when none of the process in memory is in the ready state, then the OS swap one of the block process out onto this into a suspended queue. So this is again a queue of existing process that have been temporarily kicked out of the main memory or suspended. So the operating system then brings in another process from again suspended queue, or it honors a new process request. So we have the concept again from new state to ready, suspend, block, running, etc. So in admit, we move from new to ready. Or state, event, and class. This will be event occurs from block, and then dispatch, release. So again, this is the concept here in a sense that again, we can be in a ready or suspended, a new is created, or in this case, a new process is created to go to the ready suspended state, then from there to ready, from there to running. Now, if we are doing a graduate or some course, or we are in the state of running, if we get an interrupt, we can go or suspended due to some activity, then we can move from running state back to ready or suspend state. Other than that, we release and then we exit from the program. So we can see the other state with two suspended states, from ready, suspend, and also we have block suspend. So the characteristics of a suspended process is that the process is not immediately available for execution. Also, the process was placed in a suspended state by an agent, either itself, a parent process, or the OS, for the purpose of, again, preventing, for the process or the OS, and also purpose of preventing its execution. Now, the process may or may not be waiting on an event, or the process may not be removed from this state until the agent explicitly orders the removal. So what are the reasons for process suspension? First, we have the swapping. Operating system always need to release sufficient main memory to bring in a process that is in ready state to execute. And also other OS reasons can be the OS may suspend the background or utility programs, or a process that is suspended of causing a problem. In terms of interactive user requests, a user may wish to suspend execution of program for the purpose of debugging or in connection with the use of resources. Then we have the timing, which is a process may be executed periodically. Example, an account or system monitoring process, and may be suspended while waiting for the next time interval. We also have the parent process request. Parent process may wish to suspend execution of descendant to examine or modify the suspended process, or again, to coordinate the activity of various descendants. So these are the, again, reasons for process suspensions. So here we have a process and resources. We can see the resources allocation at one snapshot in a time. We have process P1, P2, P3. P1 have a processor and IO. P2 don't have the processor yet, but have the IO. And P3 have main memory. So that will be the conclusion of our lectures. Again, these lectures cover the concept of a process. And our topic is process description and also control. So we discussed about what is a process, what are the process elements, etc. So again, wish everybody the best. Thank you.